Okay, welcome everybody. We can start the webinar. I'm Alberto Martinelli, and I'm the representative of the User Organization Committee for the Structure of Materials subtopic. As you know, the User Organization promoted this series of webinars aiming to explore the capability of the SRF beamlines. Today, we have the pleasure of participating in the webinar by Peter Glatzel, that will present the hard and tender X-ray photon-in, photon-out spectroscopy at the SRF ID26. This beamline is dedicated to X-ray absorption and emission spectroscopy of complex systems in the tender and hard X-ray range. Peter will illustrate the potential of this beamline in detail. Peter is scientist in charge of ID26 since 2004. Moreover, he is group head of electronic structure, magnetism, and dynamics group at SRF. In 2006, he was awarded of the Farrell Little Young Scientist Award of the International X-ray Absorption Fine Structure Society in recognition of his contribution in developing XAFS-related techniques such as X-ray emission spectroscopy, resonant and non-resonant X-ray scattering. After this brief introduction, I remember you all that there will be some time for your question at the end of the presentation. You can write them in the answer and question window that you can find below on the right, not right in the chat. Then I will forward your question to the speaker. So please, Peter, you can start your presentation.
Thank you very much, Alberto, for the introduction. And thanks everybody for tuning in. So I will be talking about ID26 in the next 20 or so minutes. ID26, so maybe first to tell you that we welcome researchers from all fields of natural sciences, right? So we are not focused on one particular field of research. If anybody finds the resources in ID26 interesting, we welcome everybody. The people working on ID26, apart from me, is Blanca Detlefs, who is the beamline operation manager, and Timothy is the technician. So if you want to write a proposal for ID26, contact either me, but you will probably also get in touch with Blanca or Tim for further discussion of the experimental setup and advice on the experiments. The second scientist currently is Sami Vasala, and the postdocs are Olga and Vasil. Vinod will be leaving by the end of the year, and we do a lot of. You will see this in the presentation. You will. We do a lot of sample environment, experiments that require complex sample environment at the beamline. I would like to acknowledge here at this point the group of IFATIer with Johannes, Romain, and Benjamin, who work a lot on ID26 in order to get the various sample environments going for the various user groups. And of course, there's a large number of people in the USRF support groups who help keep ID26 running. I also encourage you to have a look at this webpage there. There is an introduction to the beamline. There are some publications, general about the instrumentation at the beamline, about the techniques that we use, some recommendation for writing proposals, and for preparing the beam times, right? Gas experiments and. And if you want to get inspiration from research that was done before and is published now from ID26, the link is given here below. Just a few introduction that all of you may be familiar with photon-in, photon-out spectroscopy. So one of the objectives of my presentation is to give you maybe some ideas of what could be done on ID26. Just so very brief introduction. So the in principle only correct way of measuring an absorption spectrum is in transmission mode. We should keep this in mind. But what can also be done, right? You can look at the fluorescence line, as you all know, and you have, for example, a solid state detector, conventional solid state detector with some kind of energy resolution above 100 electron volts, and then you see the fluorescence lines. You put your region of interest around the fluorescence line and then measure the intensity as a function of incoming energy. So that would be conventional fluorescence detected absorption spectroscopy. And what we do in a nutshell is we replace the solid state detector with an anodizer crystal, right? So the result is that you improve your energy resolution by roughly 2 orders of magnitude. And what comes out there then with this improvement in energy resolution, you can resolve the fine structure here, in this case, the K alpha 1, K alpha 2 line of iron. And what you see as well, the two spectra here, you see there are two different ion coordination complexes with different ligand environment. So not only the X-ray absorption spectrum, but also the emission spectrum, they show a chemical sensitivity, right? So we have in another spectroscopic, a secondary monochromator at the beamline that reveals then the chemical sensitivity of the emission lines. But in this case, it's a difference between a high spin and a low spin compound. So how do we do this? So we have one instrument here that is for the hard X-rays. In the second experimental hutch at the beamline, there we use 5 analyzer crystals that have a bending radius. So they are spherically bent analyzer crystals between 2 meter, 1 meter, or half a meter. Anyway, anything between this distance we can use for the bending radius. The sample is positioned here on this goniometer stage, and there's a detector up there. We currently use we can use a single element detector, silicon drift diode, avalanche photodiode, but also we have now a Pilatus 100K, so a pixel detector that gives now the new experimental possibilities. When we do the experiments, then the path here is covered within the bag, the helium-filled bag, to minimize absorption. We bring these are in principle 5 independent spectrometers that we use there, and we bring the energy calibrations of the 5 crystals there on top of each other by measuring the elastic peaks. And the resolution is around 1 electron volt, right? So you go to 2 meters if you want to improve your energy resolution, to half a meter if you want to have the best detection efficiency. On this sample tower there, we can accommodate all kinds of sample environments. Obviously, the ESRF has a number of furnaces and cells for sample environments, so you can use one of the sample environments offered by the ESRF, or bring your own cell. Many users come with their own cells that are then adapted or mounted here on this stage. Yeah, we can also, I want to say, we have a lot of space here, right? Here, it's also possible to mount a magnet. For example, we mounted electromagnets there for magnetic circular dichroism studies. So there are many things are possible there on this stage that can be modified. So first, I explain a little bit or give some examples for what we do with this so-called Herft Zanes. Just as a reminder, not all of you may be familiar with this. So I give you an example here for cerium dioxide. So you look at the absorption of a 2p electron to 5d, so the L3 edge, or LH, L3 edge in our case, and then we look at the fluorescence line with our emission spectrometer and see here the L alpha 1 line from cerium. So what we do now, we scan the you can scan the incoming energy around the absorption edge, and you can scan your secondary monochromator and then plot the intensity versus those two energy axes, and then you get your so-called Rix plane. Okay. Then once you have this Rix plane, what you can do, for example, you can integrate all the intensity in this direction, and then you get your conventional total fluorescence yield L3 absorption spectrum of cerium. Or you take a diagonal cut through this Rix plane, and then you get the red spectrum here. And that is what we call the high energy resolution fluorescence detected X-ray absorption spectroscopy. Okay, so you see very nicely here that in this high resolution spectrum, you see the cerium 4f orbitals, very interesting because this is where the oxidation reduction happens in the 4f orbitals, but you also see the fine structure of the 5D band. You reveal there the crystal field splitting of the 5D band in the high resolution spectra. What you do experimentally to record such a spectrum is just you tune your emission spectrometer to the maximum of the alpha 1 line, and then you don't move your emission spectrometer anymore. You just scan your incoming energy, and out comes the spectrum. This was actually just for historical correctness. This was first done by K.O. Hämmerlein. It was published actually in 91 at NSLS1 and on dysprosium. And they saw this dramatic line sharpening effect so a long time ago. And then a few years later, Paolo Cara, he pointed then out that this is actually not an absorption spectrum what we measure. which is true. But one has to, it can be, at least in this region, very close to a real absorption spectrum or proportional to the absorption coefficient. In this range, one has to be very careful, but one can still use this, keeping this in mind for chemical characterization, right? One just has to be careful when one does the calculations. But Herft-Zanes is a very powerful technique. I give you one example here. In the setup that we also have at the beamline. So we wanted to study colloidal nanoparticles. So we have a reservoir there of the liquid with the nanoparticles. It goes through a pump, comes out through a nozzle. So it's then a free-standing jet without any capillary around, goes into this reservoir then back, and then we hit the free jet with the X-rays, and out comes the spectrum, right? The advantage there is that you can, in principle, the volume you probe is the volume that you have in the reservoir while it goes through the circle here. So here, for example, what you can do in a setup like this, you can then do in situ chemistry. You start with cerium nitrate, and then you add a base, TMAOH, and then you form the cerium nanoparticles. And you can do this there with one scan, 60 seconds. You see how the cerium 3+ then goes to cerium 4+. You can then, these are then the pre-edges here. So these are then the 4f orbitals. You nicely see how you go from the 4f1 configuration to a 4f0 configuration. And you see nicely the isospecific points, so you get very high spectral quality using this technique. And then you can also, we studied then the decomposition of hydrogen peroxide by the 3 nanometer cerium dioxide particles, and you see nicely then the spectral changes in the 4f orbitals during this chemical reaction. So just a summary for Herft-Zanes. So you get I call this the ultimate suppression of unwanted X-ray events, right? You can use in your spectrometer also silicon drift diode, for example. Then you have energy resolution also in your photon counting detector, and then you really suppress basically all X-rays, X-ray events that you don't want to see. So you really get almost background-free spectra. Since your energy resolution is achieved mainly by the wavelength dispersive optics, you have almost perfect detector linearity, apart then from effects in the electronics. You can go, and this is maybe some people think that you need concentrated samples for doing this. This is not the case. I show you on the next slide an example for a sub-ppm experiment. You want to use this technique as well if you have a challenging matrix, a high Z matrix where a lot of fluorescence lines are coming out. Since you have 1 EV energy resolution, you have the ideal sub-lifetime broadening separation of your fluorescence lines. And that gives you then the ultimate conditions for measuring low analyte concentrations in a challenging matrix. In some experiments, you are limited by diffraction peaks. Also, it has been shown that you are less bothered by diffraction peaks in a Herft setup. And also, if you have challenging sample environment, sometimes if you measure iron, you know that in a fluorescence detector, you get then intensity from your iron surroundings, right? Because the scattered X-rays, they hit the cell walls or any iron that is around the sample, gives you then also a signal in your detector. The XES instrument has a focusing geometry, right? So it really greatly reduces any contribution to your fluorescence signal from material that is around your focal spot size. And of course, I showed you then you have the sharpening of the spectral features, very important. Also point out that since you have background-free spectra, you get excellent spectral quality, and that helps you then if you want to do any statistical analysis, multivariate analysis, anything. Right? So it's easier with those Herft-Zane spectra. An example here, we can really measure sub-ppm. So this is done by Alain Manceau, did many studies on ID26. Many publications came out of this work, and within this collaboration, we developed, or mainly the crystal analyzer laboratory at the ESRF developed those half-meter bending radius analyzer crystals, increasing the detection efficiency. And with this setup, we really go sub-ppm. So 1 sub-ppm mercury-containing sample is measured in a few hours, right? And here you see the spectral differences between mercury in human hair, originating from either from the amalgam in your teeth that was removed or from eating too much predator fish. But what is, I think all of you have ideas what can be done with the high resolution Zanes But we also do non-resonant X-ray emission spectroscopy, and just want to show you what can be done with this. So one thing, you look at the K-beta lines, for example, and they have a chemical sensitivity. You see here, if you change your oxidation state, the K-beta lines change, right? It's a small change, but you can measure this very reliably and reproducibly. And that allows you then, if you quantify the K-beta lines, you obtain a signal. That's the quantification of the K-beta line. You obtain a signal that is proportional to the spin at your analyte ion. And you see there for different iron species there, this is the nominal spin, and you see for the nominal oxidation state of 2 of iron, you get a large spread of the spectral shape there of the K-beta line. So what does that mean? If you want, you can apply as kind of a calibration of your spin in your iron system. So if you have, for example, if you're sure that your iron fluoride is 2.5, that means iron 3, and your ferrocyanide is really 3D a low spin with a spin 0. So truly diamagnetic, you can say, well, I do a linear regression through those 2 points. There are some assumptions, of course, that may or may not be true. But you see that all your iron minerals that you measured before, they may be above or a few below this diagonal. Above means that your calibrated spin is less than the nominal spin, and below, I'm sorry, means that your calibrated spin is above the nominal spin. So these helps you to study covalency effects in your systems. And if you do actually DFT calculations, it surprisingly often those effects in most cases are reproduced. So it's a nice technique to also link with DFT calculations. A word for radiation damage. That's important because many people worry about radiation damage. What we do, of course, at the beamline, we have a cryostat, if the sample environment allows that, right? If you have an operando cell, you cannot use the cryostat. We always determine carefully the maximum dose we can put on the sample using Zanes, or here these are fast Zane spectra for iron 2 in solution, or this is a protein PS2. You sit on the edge and then see how it develops over time. So you do a time scan and then you determine how long you can have the beam on the sample. And then we move the beam around the sample. There are scripts for doing this. And in this case, for example, we measured K-beta spectrum. And in the red spectrum, each energy of the energy point in the spectrum is measured on a different position. These are the positions. Then after those positions have been measured, we go back to each position and just measure the absorber concentration, so the ion concentration, and then we correct, and the corrected spectrum is the blue spectrum. That looks then quite nice, right? All this is programmed and implemented at the beamline for the data acquisition and for the data analysis later. Another idea, we now have pixel detectors at the beamline, and what you can do, you can tune half of your, or let's say 2 crystals to one energy and 3 crystals to another energy. This corresponds to the 2 spectra here in your K-beta lines. If you take then the ratio, the intensity ratio of those 2 region of interests, you get a signal that is actually reflects the iron spin and oxidation state, right? So what you could do then, without moving anything, without scanning your incident beam and without scanning your emission spectrometer, because you record those 2 energies at the same time, you can scan your sample under the beam and you get a map like this. In this case, you have, again, iron minerals in different oxidation and spin states. And each color there represents a different spin state of your iron, spin or oxidation state, right? So this gives you a way of, in a stationary state, so no instrument is scanned, you can map your sample, or you can do time resolved studies and using the K-beta lines. What you can also do is you can move to higher emission energies. You go to the valence to core, then you study around the Fermi energy, your occupied and unoccupied states. And this tells you actually about the ligand orbitals around your system, okay? And in this case, in the valence to core emission spectroscopy, your emission lines there, the Fermi energy is here, and these are the emission lines. They come with the tags, so they show you what ligand you have: oxygen, nitrogen, carbon, and chlorine. So this is something that is very difficult to achieve with EXAFs, or not possible with EXAFs to distinguish between those ligands. And this you can do with valence to core emission spectroscopy. You can now combine this valence to core emission spectroscopy that I showed with the resonant excitation. And how does that work? So I go again to a 5D transition metal. Well, I go to a 5D transition metal there in platinum. So you go again to your L3 edge. So you absorb resonantly into, let's say, the white line of your your platinum. And if you look at the transition 3D to 2P, that's the L alpha 1 line. But you can also look, that would be the core emission line that you use for your Hertz spectroscopy, but you can also go to transition from a occupied valence orbital down to the 2P level. That is then a smaller energy transfer, right? Because less energy remains in the sample. And you see that the final state you end up with is a hole in the valence band and an electron up there. So this is actually an excitation that you would usually study with your UV-Vis spectrometer. And you can do this, for example, this kind of Rick's spectroscopy or valence band Rick's, if you want to call it this way, in platinum nanoparticles again. So there's the elastic peak is here at 0 energy transfer, and you have a metallic nanoparticle. These are roughly 1 nanometer particles. You see they're metallic. That means your excitations kind of they merge into the elastic peak at 0 energy transfer. And if you then expose your nanoparticle to platinum, you get those bonds between the carbon monoxide orbitals and the platinum atoms. You form bonding and antibonding orbitals, and you open up a band gap. And this opening of the band gap or of a gap there between the orbitals, you see directly then in your valence band Rig spectrum, right? You can try to calculate this with very basic DFT calculation, in this case the FEV code, and you can then reproduce quite nicely this opening of the band gap and do a quantitative analysis of the spectra. Yeah, so this just to give you some ideas. There are several beamlines at the ESRF where you can do photon in, photon out spectroscopy. That may be confusing. What should be done where? Yeah, so I list them here. So I'm representing here ID26, but there's also ID26, the RIX instrument. And there is also the branch, the DCM branch of ID24, right? I will not walk you now through all the details. The slides will be on the ESRF webpage. You can have a look, and you can visit, of course, then the web pages as well of the different beamlines. I just want to point out the important differences one is the lowest energy. So ID26 really goes to the tender X-ray range, right? Currently to 2.4, so just below the sulfur KH in the incoming beam. And our tender X-ray spectrometer can go as low as the aluminum K-alpha line. The ID20 RIGS station is specialized for high energy resolution RIGS, right? So they really allow you to start to study collective excitations, orbitons, spinons, and whatnot. So this is their specialty. Also, they have a dispersive Van Harmos spectrometer for certain applications. The ID24 DCM branch has the smallest beam size of the 3 beamlines. They can go down to 500 nanometers in the beam size, which is ideal obviously for all kinds of microscopy experiments, but also for extreme conditions, right? This is one important application there. Okay. So if you're interested, well, and you wonder which beamline is the best suited beamline for your experiment, just contact the 3 beamlines, and then we talk to each other and see what is the best place to go to. So I told you that on ID26, we go to the tender X-ray range. And for photon in, photon out experiments in the tender X-ray range, we have this setup here that was actually conceived and built within an ANR grant that was led by Alain Monceau. So this is, just to give you the dimensions, this is again 1 meter bending radius. So this is roughly 1 meter, the different distance between the sample and the analyzer crystals. We have here 11 crystals, so-called Johansen, cylindrical Johansen crystals that reflect then the beam onto the detector here. And you see this can all be is encased in a large vacuum chamber. Yeah. Despite being in a vacuum chamber, we can here on the sample stage, we can have a cryostat as well, and we can have in principle all kinds of sample environments. We are about to develop the sample environments for this that work inside the vacuum chamber, and I show in the next slide what we achieved already. So this is now for the tender X-ray range, and you see here how, again, the spectral sharpening in case of molybdenum oxide, the sharpening effect that you achieve with the tender X-ray spectrometer at the L3 edge of a 4D transition metal. I think the community there is, you're very well aware of the relevance of the tender X-ray range. You can study sulfur, but you can also for the 4D transition metals, instead of measuring the K edge, where you cannot access the valence orbitals, if you go to the L edge, you can access the valence, the 4D orbitals there, and that contain then the information about the chemical bond. And we would like to do this, obviously, in operando conditions. So in collaboration with a group of Jan de Grunwald at the KIT, we developed, or the ESRF sample environment developed this operando cell that allows you to do operando experiments in the vacuum chamber of the 10-day X-ray instrument. And the high energy resolution allows us to probe here the carbonyl species. So this is really a peak that is due to the CO bond to rhodium, and you can, by looking at the intensity of this peak, you can quantify the number of carbonyl species and make plots showing the amount of carbonyl species as a function of temperature and as a function of position there in the cell. Right, you get more carbonyl species towards the CO inlet than towards the outlet. Yeah, so we develop all kinds of sample environments there for the 10-day X-ray. If you have any requests there, we see what is possible. ID26 is also undergoing a refurbishment program that's very important. And the goal of this refurbishment program is to replace, so it concerns the pink beam mirror here, horizontally deflecting mirror, and the double crystal monochromator. We will install next year a double deflecting mirror, horizontal deflecting mirror that gives better beam stability. And the DCM will be replaced as well with a new double crystal monochromator that is developed by the ESRF. And having this setup with a new monochromator and the new beam layout with a double deflecting mirror, we will improve the beam stability, and what is very important, significantly decrease the overhead time for switching between absorption edges. Right, more and more experiments want us or proposals want us to switch between 5, 6, or even more elements, ideally quickly under operando conditions, and this will be much faster using this setup there. And well, we will also hopefully at some point in the future hope to decrease the energy of the beamline to the phosphorus K edge, and the new mirror will also collimate the beam above 10 kiloelectron volts, giving us better energy resolution and higher flux. And with this outlook to the upgrade for ID26, I thank you very much for your attention.
Thank you very much, Peter, for this nice presentation. Before starting with the discussion, I remember you all that this presentation has been recorded and will be made available on the SRF webpage dedicated to this webinar series, together with all the previous presentation. So, as I told you in the beginning of this webinar, you can write your answer in the answer and question window that you can find below on the right. And don't write your question in the chat, write in this window, and I will forward your question to Peter. So we are waiting for question. I have a question for Peter. There is a great request for beam time at your beam line.
There's yeah. I think all spectroscopy beamlines at the ESRF, there's a large number of a very large number of proposals submitted to the various beamlines, but I don't know. It's obviously not a reason not to apply, right? It's normal. It's not completely we're not swamped. It's not a factor of 6. It's between 2 and 3 the oversubscription. So it's perfectly healthy, normal oversubscription.
Okay. So that you can also analyze magnetic excitation with in your beamline, such as spinors and other kind. You can measure all kinds of this kind of magnetic excitation. There are a lot of measurements that you make about this topic.
There is, so for the magnetic excitations, so you want to do the high resolution rigs on ID20, right? So if you look for this, right? So that's a I mean, in principle, we also what we can do, we can combine rigs with the magnetic circular diachrons, and we did this on colloidal magnetic nanoparticles. You can do this. In this case, we have a phase. I didn't mention this. We have a phase plates installed at the beamline, so we can generate circular polarized light. That is possible. And then the thing is that we do not have, like other beamlines, ID12 or ID32, a dedicated magnet there that goes to 17 Tesla. This we don't have, right? So it must be a sample that we can go maybe to 1 Tesla. So it must be a sample that is magnetized at this magnetic field, right? Then there are some experiments that we can do as well in combination with the phase plates that we have at the beamline. That's also possible. But
Okay.
what you mentioned, spinons and things like this, is best done on ID20.
Okay, thank you. We have now a question by Wei Zhu. Thanks, Peter. After adding a new mirror before DCM, do you need to realign all the instrument downwards?
Yes, that's a good question. Yeah, that's a big project. So by changing the beam path, so going from a single deflecting mirror to a double deflecting mirror, the beam path changes, and all elements downstream have to move horizontally first. And when we change the DCM, they also have to change vertically. They have to move up vertically by 15 millimeters and horizontally, depending on the position where we are. But this can all be done. It's all calculated and all in the works and all prepared. We're just waiting for the mirrors and the monochromator to arrive at the EHF, and then we're ready to go. So it can all happen in 1 or 2 months. This will be installed. First the mirror in 2025, and then the monochromator in 2026. But it's true, it's a big project. Many things have to be changed.
Okay. Another question by Ishu. Thanks. Another question for 2-meter spectrometer. Does HARAD XAFs benefit from energy resolution with respect to 1-meter spectrometer?
Yeah, it's to what extent, that's also a good question. To what extent your instrumental resolution, you say the line width that I observe here, the width or the instrumental resolution that I achieve in order to measure the line here, to what extent that influences then the energy resolution in my Hertz-XAS spectrum, if I understood the question correctly. It's a tricky question. It depends a lot on the core lifetime broadening of your intermediate and final state. So I cannot give you a clear answer. I make the statement here that your instrumental resolution should be below the core lifetime broadening. Yes, that it should be like this, but you already get some kind of spectral sharpening if you're a little bit larger than the core lifetime broadening. It's really there are various factors that play in. It's very difficult to give a clear answer. For sure, your instrumental resolution should be on the order of a few electron volts and not 10 or 15.
Okay, there is another question by Daniel Canoblanco. Thanks for the talk. I was wondering what are the negative aspects of measuring in HARFD in comparison with conventional XAS?
What are the advantages or?
What are the negative aspects?
The negative aspects.
Yeah.
The most important negative aspects, again, very good question. The most important, it's a fluorescence detection method. That's why we call it HERFD, so high energy resolution fluorescence detection. We don't like to call it partial fluorescence yield because it is a fluorescence detected method, and for every X-ray absorption person, when you hear a fluorescence detection, you think self-absorption effects, right? So since it is fluorescence detection, you always have to worry about self-absorption effects because it's not transmission, it's fluorescence detection. So that is the so if you compare, right, transmission with HERF, then transmission, you have other maybe problems, pinhole effects, or but you do not have the self-absorption. So you either you try to correct for it, or you say you accept it, or and all your samples have the same degree of self-absorption. You have to worry about it, and you have to mention it in your publication that this is something that you have to worry about when you compare the spectra. Is there any other disadvantage in principle? Well, not. I wouldn't. The instrumentation is different, but I wouldn't say it's much more complex. I would not say the spectrometers, once it's mounted, set up, and the macros are written, it's not very complex to set up or to switch crystals. Is very fast, right? So the one advantage, or maybe I should say this, obviously, if you don't get an MCA spectrum out, right? If you put your energy resolving detector next to your sample, you get the fluorescence lines of all elements in a simultaneous fashion. And that's not so. For an MCA analysis, you would have to scan your spectrometer through, and the scan range, the energy range is quite small for a given crystal reflection, right? So that's also, it's not really made for fluorescence analysis. If you really want to measure, I don't know, have 10 different samples in your sample and you want to get a fluorescence line, that's not what you, maybe not. Maybe with our TEX instrument, you could do this because the angular range is very large.
Okay, thank you. There are some other questions. Seems not. So we can close the registration here. And I thank you again. I remember you all that the next Thursday, the 21st November, and will be held by Didier Vermeil, that will present the XMAS BM28, the UK materials science beamline at the SRF.